Okay, here we're moving a bit closer to the kind of wording you see in exams. So, if we read this through, we've got a question about mass-produced glass jars having flaws, and we see use a distributional approximation. Now, in this particular page of this particular booklet, we kind of know what approximation it's going to be. But in an exam, you won't know that, so you have to read really carefully and decide what kind of distribution is relevant. So you have to be able to see that what we're doing is we've got 180 jars, and we are counting the number of flaws in amongst those 180 jars. And the probability of each jar having a flaw is this, which is a fixed probability. So we've got a fixed value of P, a probability. We've got a fixed number of trials, jars, so we've got a value of N, and we are interested in whether there are three or more flaws, sorry, more than three flaws, so we're counting the number of flaws. So therefore we can recognize this as being, if X is the number of flawed jars, then X has got a binomial distribution. Okay, and for a binomial we need an N and a P, and we've picked up that that's 180, and this is 0.02. Okay, so we have to use our intelligence to set up the original distribution, and in an exam you won't know that you're expecting it to be a binomial distribution. Okay, then we've got to use an approximation. So at this point we only know one approximation, and for the approximation we know we need to a large value of N and a small value of P. So we say N equals 180, which is large, and P, which is 0.02, small. Okay, the question may or may not ask us to justify our approximation, but we should always check that, because there's another approximation coming that that works when P is close to 0.5 or when P is not particularly small. So for N is 108 is large, P is small, so we can use a Poisson approximation. Okay, which we were kind of expecting. So how do we set up a Poisson? Well, our approximate X is going to twiddle a Poisson, but we need a lambda value for our Poisson. And we know that this lambda is the mean of the distribution. So we need to work out the mean of the original distribution. So the mean of our binomial distribution, we have a formula for mu, which is in the formula book. The expectation of X, which is the same thing as the mean, the formula is NP for a binomial. So that is 180, because that's our N, times 0.02, 0.02, okay, which is 3.6. if you do that on your calculator. So our approximate distribution is going to be Poisson, and now I know the mean, so my lambda value is 3.6. Okay, so therefore from our calculator we just need to work out the probability of X being the correct thing. So we want there to be more than 3 flaws. So the probability of X being greater than 3. Well, we need to diagram our outcomes. 0, 1, 2, 3, 4, ... We want to be more than 3. So 4 is good, but 3 and all of these ones are bad. Everything from 4 onwards is good. Okay, so I need a big box and a little box. Whoops, no. I want to separate the 3 from the 4. So therefore I need to do the probability of everything, which is 1, minus the probability of X being 3 or less than or equal to 3. So this gives me what I need to enter on my calculator. So distribution, second page, Poisson CD is the one we not always use, variable, so we've got an X value of 3, and we're using a lambda value of 3.6, if I can key it in correctly, 3.6, okay, probability of X being less than or equal to 3 is 0.5152, so we need to do 1 minus 0.51522, which is 0.48478, and that is our answer. Okay, we'll probably get away with 3 significant figures, but that's probably what the guys using tables will get. Okay, all right, and on to part B. So part B, hopefully, is something looking very similar. Okay, so we've got light bulbs packed in boxes of 60. Okay, so we're taking 60 light bulbs at a time, and we've got a percentage of light bulbs braking during shipping. Once again, it's a distributional approximation, and we've got a fair idea which one it's going to be. Okay, and we want the probability that 2 bulbs from a box break. So we're kind of expecting, because of where we are in the booklet, this to be a particular distribution. But I suggest, actually, given that you know that it's going to be a bit like part A and we kind of know what distributional approximation, why don't you pause this video right now, okay, see if you can set up a binomial distribution and convince yourself that is the correct distribution, and then turn it into a Poisson distribution, so you'll need a lambda value, and draw your diagram and see if you can get an answer, and then just check that the answer corresponds to the solution I'm about to go through. So you just go away and do it, okay, on a scrap of paper, and then I'll write it up beautifully for you, and you can put the beautiful version in your notes. But if you can convince yourself you can do it, so pause the video, right, go away, okay? I don't want you to come back, I want you to pause now. Yes, so you've gone, all right, okay, right, you're back now, that means you've tried this, okay, so here's how you do part B. So you'll have said that the number of braking is X, or Y, you may have called it. Okay, so X is the number that break. Sorry, number of light bulbs that break. Always explain yourself clearly, okay, and in better writing than I've used. So X is the number of light bulbs that break. So X, well, we're counting the number of light bulbs out of 60 light bulbs, so it's a binomial with n is 60, okay, and the probability of each light bulb breaking is, well, the 2% of them break, so the probability is 0.02, and we want the probability that more than 2 break, so the probability that X is greater than 2. All right. Okay, but we're not going to use the binomial distribution, though we could. It says in the question we have to use a distributional approximation. So once again, we can say that n is large and p is small. That's our justification. So therefore, we can use a Poisson model to approximate this. So therefore, approximately, X has a Poisson distribution, okay, but we need to know its lambda. Okay, so coming back for this, we need to know the mean of our binomial. So our mean is NP, which is 60 times 0.02, which is 1.2. So we've got Poisson with mean 1.2 with a lambda value of 1.2. So on our calculator, well, we need to draw the diagram first. So I want the probability of X being greater than 2. So 0, 1, 2, 3, ... I can have 0, I can have 1, but it's got to be greater than 2, so I can have 2. Okay, but I can't have 3 or anything else. So big box minus little box. So I'm going to be doing 1 minus the probability of X being less than or equal to 2 on a lambda value of 1.2. So I need an X value of 2 and a lambda value of 1.2. So that's a probability of 0.87948, and that's what I need to take away from 1. So I need to do 1 minus 0.87949, which gives me 0.1205 to 4 significant figures, which will be fine. Okay, so that's how you do the Poisson approximation to a binomial distribution.